Welcome to our lesson on perpendicular and angle bisectors. Let's start by talking about the perpendicular bisector theorem and its converse. First, we need a quick definition. That is the definition of equidistant. Kind of self-explanatory. Equa is part of equal, distant, distance. So therefore we're talking about something that is the same distance away from other things. So for example, in our figure here, you will notice that point P happens to be about 5.5, actually it's a little bit more than 5.5, so let's go with 5 55/100 centimeters away from point A. You will also notice that point P happens to be about 5 55/100 centimeters away from point B. So therefore we say that P is equidistant from points A and B. Really quickly, I want to go through and show you something rather interesting here. First, let's draw in segment AB. What I'm going to do is I'm going to construct the perpendicular bisector to AB. So I'm going to put my compass on point A and draw an arc that extends over halfway across the segment. And then using that same setting, the same radius, I'm going to put my point of my compass on point B and draw an arc across the segment there. And of course, through the points where those two arcs intersect, I'm going to draw a line. So once again, this is the perpendicular bisector of segment AB. So line PE is perpendicular to and bisects segment AB. And notice where point P is, sitting right there on the perpendicular bisector. Now remember, because of the way a compass works, that every point along this arc is exactly the same distance away from point A. So these 2 points where the arc intersects the perpendicular bisector are the same point away from A. And same with all the points along this arc. They are all the same distance away from B. And because the same setting was used for both arcs, these 2 points where the arcs intersect are the same distance away from both points A and B. Now what we're going to do is show that any point on the perpendicular bisector is the same distance away from A and B. Yes, we are going to prove a theorem. We already know that segment AE and segment BE are congruent by definition of bisector. We also happen to know that angle PEB and angle PEA are right angles, and by the right angle congruency theorem, we know that they are congruent. But we also happen to know that segment PE is congruent to itself by the reflexive property of congruence. Now, if we were to just simply draw in segments AP and segments BP, what would we know about these 2 triangles? By side, angle, side, we would know that these 2 triangles were congruent. And therefore, segment AP is congruent to segment BP. So it doesn't matter where P is, if it's on the perpendicular bisector, it is going to be equidistant from the endpoints. Which brings us to our first theorem, which we call the perpendicular bisector theorem. If a point is on the perpendicular bisector of the segment, then it is equidistant from the endpoints of the segment. So here, since we know point P is on the perpendicular bisector of the segment, we know that segment AP is congruent to segment BP. Another way to say that is the distance from A to P is equal to the distance from B to P. Now, along with the perpendicular bisector theorem, we also have its converse. Its converse reads, if a point is equidistant from the endpoints of a segment, it is on the perpendicular bisector of the segment. So since we know that point P is equidistant from points A and B, then we know that point P is on the perpendicular bisector of segment AB. So how does this help us, you ask? Well, let's take a look at this problem. What is the length of segment PR, or RP? Well, looking at our figure here, point R is on the perpendicular bisector of segment PQ. Since point R is on the perpendicular bisector, it is equidistant from our two endpoints of P and Q. That means that the distance from P to R is equal to the distance from Q to R. So there's an equation that states what we need. And now we can use the substitution property of equality to substitute in the values. Distance from P to R is 7x minus 32, and the distance from Q to R is 5x plus 18. Using the subtraction property of equality, I'm going to subtract 5x from both sides of my equation. And notice I'm saying both sides of the equation. And then I'm going to use the addition property of equality and add 32 to both sides of my equation. And finally, I'll use the division property of equality to find out that x is equal to 25. Are we done? If you said no, good job, because our instruction was to find the length of RP, which means that we now need to take and plug our x into the expression for segment RP. So the distance from R to P, or the length of RP, is going to be 7x minus 32, but we just found out that x was 25, so RP is going to equal 7 times 25 minus 32, and that is going to take a little bit of calculation. And so that should be 143. And of course, 5 times 25 is 125, plus 18 is 143. So since we're getting the same value for both expressions, we're probably correct.